Hello friends, today's topic is the pH scale. In order to represent the hydronium ion concentration more conveniently in terms of molarity, scientist name Sorensen introduced a logarithmic scale known as the pH scale. Okay, so we know that we have heard about the term pH scale, pH of a particular solution of or the component. The pH of a solution is defined as the negative logarithm to the base 10 of the activity of hydrogen ion. The pH of a solution is defined as the negative logarithm to the base 10 of the activity of hydrogen ion. Okay, so to find out, we have heard about already about pKa and pKb values. So P stands for the negative logarithm. So pH stands for negative logarithm of pH stands for negative logarithm of hydrogen ion concentration. So to explain the character of a solution of or compound, that character in the sense it is acidic, basic or neutral species, we can make use of the scale pH scale. It is having values starting from 0 to 14. If the pH is middle, that means pH is equal to 7, then the solution is said to be neutral. If it is below 7, it is acidic, or greater than 7, it is basic in character. For a very dilute solution, that is the concentration of solution is smaller than 0.01 molar, then the activity of hydrogen ions becomes equal to its molarity. So for us, in calculation purpose and all, we are not using activity of hydrogen ion because we have no idea about hydrogen ion activity. So instead of activity of hydrogen ion, we are making use of which one, the term molarity. So very dilute solution, activity of hydrogen ion is converted into molarity, so that we can say that pH of a solution is equal to minus logarithm of hydrogen H plus ion concentration, or log 1 by H plus ion concentration. Okay, since pH scale is a logarithmic scale, so a decrease of single pH unit corresponds to 10-fold increase in acidic character. That is why change in pH with the temperature is often ignored. So we are not considering that a temperature dependence on the pH, because pH scale is a logarithmic scale. So a decrease of single pH unit corresponds to 10 folds increase in acidic character. So we are ignoring the pH dependence with the temperature. So for us, we have to use the formula pH is equal to minus logarithm of H plus ion concentration, or which is equal to log of 1 by H plus ion. That formulas can be seen on screen. That is pH equal minus log activity of hydrogen ion, or which is equal to minus log H plus ion concentration. Or if you know the pH, we can calculate the hydrogen ion concentration as H plus ion concentration is equal to RD logarithm of the pH value. So if for the exam they will be asking two type of question, either they will be giving that H plus ion concentration and we are supposed to find out the pH, or pH value they will be giving, we have to find out H plus ion concentration. An acidic solution of HCl concentration is given 10 raised to minus 2 molar will have a pH is equal to 2. That means 10 raised to minus 2. If you are taking the logarithm of 10 raised to minus 2, we know that minus 2 log 10, actually minus log 10 is equal to 1, so that the pH of the solution is equal to minus will be cancelled and it will become positive, so that we will be getting the pH of the solution is equal to 2. Similarly, pH of a pure water, that means concentration will be equal to minus log 10 to the power minus 7. How did you get 10 raised to minus 7? We have learned already ionic product of water. A hydrogen ion concentration and hydroxyl ion concentration is equal to 10 raised to minus 7 at 298 Kelvin. So we have taken that value for hydrogen ion concentration as 10 raised to minus 7. So here also to log 10 raised to minus 7 is equal to 7 log 10. Minus 7 log 10, log 10 again it is equal to 1, so that it will be equal to 7, so that we can say that water having the pH equal to 7. Thus water is a neutral species, we know. Similarly, a basic solution of NaOH having the concentration of hydroxyl ion, that is OH minus ion, if it is equal to 10 raised to minus 4 molar, and hydronium ion is equal to 10 raised to minus 10 molar, then it will have a pH is equal to 10. Okay, So what will at 25 degrees centigrade or 298 Kelvin, pure water also will be having the concentration of H plus S equal to 10 raised to minus 7. Once again, a basic solution. We are calculating that pH of a basic solution. We know basic solution pH will be always greater than 7. So how will you find out that NaOH whose concentration of OH is taken, OH minus concentration is equal to 10 raised to minus 4 molar, and water hydronium ion concentration is equal to 10 raised to minus 10, then it will have the pH of a 10. That means it is a basic solution. Okay, so using this formula, simple formula, pH is equal to minus logarithm to the base 10 hydrogen ion concentration, we can calculate the pH of the solution. And always keep in mind pH, if it is equal to 7, it is a neutral species. If it is below than 7, we can say that it's acidic. If it is greater than 7, it will be a basic solution. So that is the information that we are getting from this pH value. Okay, and we are taking only the H plus ion constant. That is also very important. Just like pH indicates, we know at hydrogen ion concentration. Similarly, we are having one more term, that is POH. POH indicates the concentration of OH minus ion. So what's the relationship between pH and POH? That means we are adding this pH value and POH value, we should get the value as 14. So that's the relationship between pH and POH. Once again, pH indicates the hydrogen ion concentration. Similarly, POH indicates the OH minus ion concentration. So the what's the relationship between these two? pH plus POH will give you that 14. And if it is a solution is having pH is you can see the table, pH is equal to smaller than 7, then the value is acidic. But for acidic solution, pH will be greater than 7. Is it clear? Similarly, for a basic solution, pH will be greater than 7, but pH will be smaller than 7. For an for a neutral solution, pH and pOH will be equal to 7. In this column, it's written as pH again, it's mistake. pOH is equal to 7. Okay, so for the exam, they'll be asking the value of NaOH solution, pH value of NaOH solution. So it is a base. So what we'll do, we'll be finding out the pOH concentration, just similar to the pH itself, and using this formula, which formula pH plus pOH is equal to 14, we can find out the pH of the solution. Otherwise, it will be a raw. Okay, so if I try, the measurement of pH of a solution is very essential, as its value should be known when dealing with biological and cosmetic applications. So the pH of a solution can be used by different method. One of the method, chemically the value can be calculated by the formula we have seen already, or else we can make use of the paper which is known as pH paper. And when we are having one solution, we are supposed to find out the pH of that solution. What we will do, we will be dip that pH paper into the solution, so that there will be a development of particular color. We are comparing that color with the pH paper. Okay, so we'll be having a color chart of pH. So from that, which is more ideal or which is more matching, so using that method we can find out the pH of the solution. That figure is given in your chapter 7.11, that is pH paper with the strips, with 4 strips that may have different colors at the same pH. So what we'll be doing, we will be taken one solution which we are supposed to find out the pH of the solution, and we are dipping the pH paper, so that on the pH paper there will be development of a particular color. We are comparing that color with the color chart which is given. So we will be, from that we will be finding out the pH of the particular solution, but it will be giving only an the average value or a general idea about the pH. It won't give the exact value of pH. For a greater accuracy, pH meters are used. pH meter is a device that measures the pH dependent electrical potential of the test solution within 0.001 precision. pH meters of the size of a writing pen are now available in the market. So we can find out the pH of the solution in that method also. So usually we are make use of this equation to get the exact value of the pH, or else you can find out the pH using a pH paper method, but it's a very not convenient method, because it will not give the exact value of the pH. It will be giving that a particular range of that pH value, whether it's acidic or whether it's basic. We will not be getting an idea, but exact value 4.1, 4.2, like that pH of the solution cannot be calculated by the formula, by the electrical pH paper. or else we can make use of pH meters. In addition to that, we are having a universal indicator. Universal indicator is also there. So the same thing itself, we are adding 1 drop of universal indicator into the it's a solution into that sample solution. So what will be having, a color will be formed. We will be comparing this color with the color chart as we said before. So there are different methods of finding that pH of the solution. So here we are making use of that equation only. pH is equal to minus logarithm of hydrogen ion concentration. Okay, and we are having one problem, that is in text question 7.17. Calculate the pH of 1 into 10 raised to minus 8 molar solution of HCl. We know HCl is an acid, so the concentration of, the pH of the solution should not be greater than 7. That we should have an idea in your mind. And the concentration of hydrogen ion concentration is given as 10 raised to minus 8 molar. So we are making use of the formula, simple formula. pH is equal to minus logarithm. For very dilute solution, we have mentioned that pH of HCl solution. So solution we will be having water also. So hydrogen ion concentration from water also will be taken as 298 Kelvin. So that will be equal to 10 raised to minus 7. Okay, and the HCl concentration is given, H plus concentration is given as 10 raised to minus 8. So total H plus ion concentration will be equal to 10 raised to minus 8 plus 10 raised to minus 7. So that we'll be getting the value of pH is equal to 6.99. Once again, in this question, they are mentioning about HCl solution. Solution in the sense HCl plus water, is it? So in water also H plus ion concentration will be there. As the same time, HCl also H plus ion concentration is there. So in this question, from the HCl, H plus ion concentration is equal to 10 raised to minus 8. Water, we should know that is 10 raised to minus 7 at 298 Kelvin. So we have to take the sum of 10 raised to minus 7, 10 raised to minus 8, and we have to find out the. Okay, so that should be keep in mind. Second question 7.16. The concentration of hydrogen ion in a sample of soft drink is equal to 3.8 in 10 raised to minus 3 molar. What's its pH? So there is no make use of that water. We are not supposed to consider that concentration of H plus ion concentration from that water. So we will be taking directly pH is equal to minus logarithm of H plus ion, that is equal to minus log of 3 into 10, 3.10 into 3.8 into 10 raised to minus 3, so that the value will be equal to 2.4. That means it is slightly acidic. It is slightly acidic. Once again, even the question is like this, that means HCl solution of, if they are clearly mentioning about the solution of one particular component, then we should take that concentration of H plus ion from that water also, that is 10 raised to minus 7 at 298 Kelvin. Otherwise we are not supposed to. Okay, next we are having in text question 7.18. The ionization constant of HF is equal to 3.2 into 10 raised to minus 4 molar ionization constant. Okay, and calculate the degree of dissociation. That is degree of dissociation, we know that is alpha of HF in its 0.02 molar solution. Calculate the concentration of all the species present. All the species present means H3 positive, F minus, and HF in the solution, and its pH also can be calculated. So almost all the details what we have learned in the last video and this class pH of the solution, we have to use of all these informations together. So ionization constant means, since it is HF is an acid, we can say that it is Ka, ionization of a weak acid. So Ka is given, ionization constant, that means dissociation constant alpha has to be calculated, degree of dissociation alpha has to be calculated, along with that one concentration of all the species present in the reaction medium plus pH. So many details we have to calculate. So what is the first procedure? That is, first step is that we will be writing that dissociation of that HF. So that HF will undergo dissociation in water to form hydronium ion and fluoride ion. Under that, as we do usually, that initial concentration has to be written and equilibrium concentration. Okay, so initial concentration is given as 0.02 molar. So we have written 0.02 molar solution, 0.02 molar. Okay, they have given that capital letters molar. In this question, it's written by mistake smaller m. So that should be 0.02 molar. Okay, so actually it is molar and initial concentration product will be taken as 0. Equilibrium concentration we usually take C into C minus C into 1 minus alpha. So C is equal to 0.02 we have written, and other products will be C alpha, that is 0.02 alpha and 0.02 alpha. So Ka, that which is given as 3.2 in 10 raised to minus 4, we are making use of that formula itself. That means, and then concentration of hydronium ion concentration into that of fluoride ion divided by HF. Find out the value so that the alpha will be getting, so rearrange the equation and find out the value of alpha as equal to 0.12. You have to make use of that knowledge that you are having, that quadratic equation, solution of a quadratic equation. We will be getting quadratic equation and solve the value for alpha, so that alpha will be is equal to 0.12. And from the equation it is clear that hydrogen ion concentration and fluoride ion concentration both are equal to 0, which both are equal, which is equal to C alpha. C is equal to 0.02, alpha we have calculated 0.12, so that we are getting the value 2.4. Okay, that is 2.4 in 10 raised to minus 3. And we have to calculate the concentration of HF. HF is equal to 0.C into 1 minus alpha, the formula. C is equal to, concentration is equal to 0.02. Alpha we have calculated as 0.12. So you just substitute so that the equation answer will be equal to 10 raised to minus 6 into 17.6 into 10 raised to minus 3 molar. And we have to calculate the last term, that is pH of a solution also has to be calculated. We know the equation pH is equal to minus log H plus ion അല്ലെങ്കിൽ minus log H3 positive, both are equal we know. So we are just substituting that value of hydronium ion, that is minus logarithm of 2.4 into 10 raised to minus 3, so that the answer will be 2.62. Once again, in this question we are making use of all the knowledge we are having about that ionization and degree of ionization and pH of the solution. Try to do. Now we are having some homeworks. Exercise question 7.42. The pH of a sample of vinegar is 3.76. Calculates its hydrogen ion concentration. So pH is equal to minus logarithm of H plus ion concentration. pH of the solution is given. So we will be finding out the anti-logarithm of 3.76, so that we will be getting hydrogen ion concentration. Try to solve that question in your notebook. Second question, assuming exercise question 7.48, assuming complete dissociation, calculate the pH of the solutions. They have given the concentration of that H plus is given 0.03. So complete dissociation in the sense they are strong electrolytes. They are strong electrolytes, so that means there is no water at all. So we can say that you can make use of this formula directly. And along with that one, we are having that exercise question 7.45 for 7.55 and 7.56. Okay, so try to solve that homeworks and find out the answer in your notebook. Okay, our next topic is common ion effect, very important. That is the degree of dissociation of an electrolyte or a weak acid or weak base is suppressed in the sense reduced by addition of another electrolyte containing a common ion. As this happens according to Le Chatelier's principle, this phenomenon is known as common ion effect. Very simple concept. From the definition, it's very complicated, you may feel, but it is a very simple one. Considering we are considering an dissociation of weak acid, that is acetic acid. CH3COH is acetic acid. It will be dissociating as CH3COO minus, that is acetate anion and H plus ion. That's very simple. If you are adding another reagent, which furnish acetate or H plus, which furnish H plus or acetate anion, that for example ammonium acetate. Ammonium acetate will dissociate as ammonium NH4 ions and acetate anion. So in the reaction medium, acetate anion is getting increases, because acetic acid we are getting acetate anion. At the same time we have added ammonium acetate. So what will happen? Acetate again, at the concentration of acetate anion will be getting a increase. So that means right hand side is getting increases, the product concentration of the product is getting increases. So what will happen? The backward reaction will be taking place according to Le Chatelier's principle. Backward in the sense the dissociation, complete dissociation will not be taking place. The dissociation will be suppressed or reduced by the addition of another electrolyte which is having acetate anion, or else you can add any other reagent which is having H plus ion also. The same thing will be happening then also. That means this effect is known as a common ion effect. Another example, if you are considering, we are taking ammonium hydroxide and ammonium chloride. Ammonium hydroxide will dissociate as NH4 plus and OH minus ion. So ammonium ion and OH minus ion is there. We are adding another electrolyte, that's ammonium chloride, NH4Cl. Up it will dissociate as NH4 plus and Cl minus ion. So in the reaction medium, the concentration of ammonium, because both are having the common ion ammonium, that ammonium ion concentration is getting increases, that is product side. So according to Le Chatelier's principle, what will happen, that backward reaction will be taking place. That means equilibrium will shift towards the unionized species. That means backward reaction will be taking place. So in general we can say that if you are adding any reagent which is having the common ion to a particular species, that degree of ionization will be suppressed. This effect is known as common ion effect. Our next topic is buffer solution. What do you mean by buffer solution? The definition is like this: the solution that resists change in pH on dilution or addition of small amounts of acids and alkalis are called buffer solution, and this ability of resistance is known as buffer action. For example, we are having one acid, HCl acid is there, and it will have a definite pH. If you are adding any other reagents, that means for example NaOH we are added, so neutralization will be taking place. So what will happen, the pH of the solution will be changing usually. But there are some solution, even though we are adding any other acids or alkalis or water itself, there will not be change in the pH of the solution, and such solutions are said to be a buffer solution. Buffer solution is having a large number of applications, but we are telling the definition: buffer solution, so solution which can resist the changes in pH on addition of any other reagent. Very important. For unit, very important one. Okay, next one, types of buffer solution. Buffer solutions are classified into three. First one is natural buffer. What do you mean by natural buffer? It is the salt of a weak acid and weak base. It is a salt of weak acid and weak base. For example, ammonium acetate. Ammonium acetate will be formed from ammonium chloride or any other salts of ammonium weak salt. Then along with that one, we'll be doing acetic acid itself. Acetic acid is a weak acid, and another any ammonium solution that is a weak base we have to take. So that will be mixing together. So neutralization will be taking place, and we'll be getting a salt. And that salt is an example for natural buffer. Second one is acidic buffer. What do you mean by acidic buffer? It is the mixture of a weak acid. It is a mixture of a weak acid and its conjugate base, or salt with a strong base. For example, boric acid and borax, or second one is phthalic acid and potassium acid phthalate. Potassium acid phthalate. Okay, pH of the acidic buffer is given by in the equation known as Henderson equation, which is equal to pH is equal to minus logarithm of salt concentration divided by acid concentration. So that is very important. For the exam they will be asking what you mean by buffer solution, classify or the buffer solution. The first one is natural buffer and second one is acidic buffer. Acidic buffer is the mixture of a weak acid and its conjugate base. Okay. Then third one, a basic buffer. It is the mixture of a weak base and its conjugate acid, or its salt with a strong acid. So what is the difference between acidic and basic buffer? Acidic buffer, that is acidic buffer, it is a mixture of weak acid and its conjugate base. Here a basic buffer, weak base and its conjugate. Again, that example is that ammonium chloride and ammonium hydroxide, glycine, it's mixture, then glycine and glycine hydrochloride is an example for what basic buffer. So again in the case of basic buffer, we can make use of the equation, Henderson equation itself. So instead of pH we are calculating POH. POH is equal to logarithm of concentration of salt divided by concentration of base, and from that we'll be getting pOH. Since it is a basic buffer, we'll be getting pOH, so we will have to make use of the formula that we have learned already. pH plus pOH is equal to 14. From that, pH can be calculated as 14 minus pOH value. So hence this equation for the basic buffer is written as pOH is equal to minus, sorry, logarithm of concentration of salt divided by concentration of the base. So what is the question? Why pH of our blood remains almost constant at 7.4, though we quite often eat spicy food? Even though we are having spicy food, why we are our pH of our blood is remains constant? The answer is blood is a buffer containing carbonic acid and bicarbonate anions. Small amounts of acids or base produced from the spicy food do not disturb its pH. For the exam, you can expect such a question: why the pH of blood or human blood remains constant even though we are having spicy food? The answer is that blood is a buffer. That means it can resist the changes in the pH. It's a buffer of carbonic acid and bicarbonate anion. Small amounts of acid or base produced from the spicy food will not disturb the pH. Okay, so in this class we have learned about pH determination and buffer solution. Watch the video, prepare notes and study.